Okay, thank you, Rick, for the nice introduction, and thank you for the invitation. So I can see already some sleepy eyes, and hopefully by the end of this lecture, all of you will be awake. And so, yeah, so what I'll be talking about that possibly already you are hearing from the very first day. In the effective field theory, one of the important aspects is basically how do you construct those effective operators, right? So it's audible, right? Yeah, okay. So now, in the morning, if you listen carefully, this Tim's lecture, he has talked about SMEPT and HEPT and all those things. So the method that I'll be talking about, though the primary intention would be to show you how to construct those operators, okay? But that is certainly not restricted to only the construction of the SMEPT, right? But also different variants of the effective action, effective operators you can write down. For example, the HEPT operators and in the context of chiral Lagrangian effective operators, those also you can generalize that thing. But as I mentioned, the primary interest would be towards the SMEPT, right? So now, if you think about what kind of method you should use to construct these operators, we'll try to use some method which is very much familiar to you, because in the quantum field theory, or if you're familiar with the standard model, when you write down the Lagrangian, you basically write down those operators, right? For example, the kinetic term of the scalar fields, kinetic term of the fermions, Yukawa interactions, and so on. And if you just try to look back, what was the ingredients when you try to write them down, then you'll find out there are some kind of degrees of freedom. And in the context of EFT, what Brando and team, every one of us were talking about, there was a lighter degrees of freedom. So we'll decide what are my lighter degrees of freedom, and then we'll talk about the symmetries. Okay, so if we have the information about the symmetry and this lighter degrees of freedom, then we can construct the operators. Now the question is basically, okay, fine, if we construct the operators, is that sufficient for us? The thing is basically no, because we are interested in something more. That is not only the operators, but also to form an operator basis. Now, as you know, from the concept of vector space, that when you talk about the basis, it automatically there is no redundancy, right? So it may happen when you construct those operators, though appearance-wise or looks-wise, for example, what Tim was also discussing, that two Lagrangian, okay, they look different to you, but there is certain kind of field redefinition he can make, and you can understand there is a, you can go from one theory to another theory. Similarly, it may happen with some operators or multiple operators. They structure-wise, their looks to be different, but they are related to each other. For example, either equation of motion, or by the integration by parts, or even the pairs and different kind of transformations. So we have to be careful after constructing the operators that we should remove those redundancy such that we can create an operator basis. Our primary interest will be to construct the operator basis, right? Now, the formalism that I'll be talking about will be completely driven by the symmetries. So you can understand in the particle physics, when you talk about the symmetry, the group theory, the representation, all those things comes into the picture, okay? But what we'll try to do, instead of going into very mathematical detail, we'll try to use mathematics in a much more intuitive way, such that at the end of the day, we are not lost in the mathematics, rather we are in a position to compute effective operators for any kind of given theory and for given quantum fields. That is our target, right? So now, to start with, we should understand what are the ingredients or the bricks or the quantum fields we should be talking about. Let me write down them. It is visible? Okay. So I restrict myself to work on 3+1 dimension space-time, okay? But again, this is just to make our life easy, but certainly this is not this method is not restricted to this, and I'll make a comment exactly where you can generalize this thing for any space-time dimension. Okay. So now the Lagrangian density, if you think of the mass dimension, is 4, right? So now the operators are consist of basically my scalar field, okay, and then I have a Fermion field, okay, and then you can think of some gauge field, and if we want to do in a covariant way, so instead of a normal derivative, what we will talk about the covariant derivative, right? And also we have some stress tensor F mu, right? Now, among all these, what we'll do, we'll try to formulate this operator construction in a covariant way, and also the construction should be consistent with the gauge invariance. Okay, and that is the reason we will not include in our construction mu as an explicit quantum field. The presence of mu will be masked within the covariant derivative, okay, and also in this F mu. So you will not find out any operator where mu is explicitly there. Okay, so to construct those operators, our interest is basically in the scalar field, Fermion field, covariant derivative, and the field tensor, right? Now let's look at the mass dimensions of these fields. So what is the mass dimension of scalar field? That you already know, which is 1, for Fermion is 3/2, covariant derivative is 1, and F mu is 2, right? So now, as Tim has mentioned already, that the renormalizable part Lagrangian, if you write down for the standard model, you will restrict yourself to dimension 4 operators, right? And then what you do, you write down basically dimension 5 operators, dimension 6, and so on. Now there are 2 concepts are here. One is operator class, and this is the operators. Operator class and operators itself. Now, what are the operator class? The operator class, if you start with these 4 configurations, okay, so then each mass dimension, how many Lorentz invariant structures you can construct, that will give you the operator class. For example, if think about the renormalizable part, okay, so what are those? I have a phi 4, right? I have a psi square phi. Okay, so now you see, when I'm writing the operator class, I am writing in terms of polynomial. I am not worried about whether I'm writing a psi bar, psi phi, proper Lorentz scalar, so on. I am not interested in that way. So that's why this construction will be in terms of polynomial. So what I'm translating now, the definition of a Lagrangian from a proper covariant form to a polynomial. So for me, in this construction, this nomenclature is important. Is a symmetry invariant polynomial. Okay, so in this way we will see that what are the possible every mass dimension, how many different Lorentz invariant this kind of polynomial I can write down. Those are basically my operator class. Now it may happen, and we'll see that, for example, in a standard model, psi square phi is the operator class, but what kind of fermions you have, right? For the quark fields, for the leptons, and the Higgs, right? So you have multiple operators within this class. So the mapping is basically within an operator class, I can have multiple operators. Okay, so the process is basically you look for the symmetry. Okay, using that symmetry, you first identify what are the operator classes. Okay, and then within that operator classes, how many operators will be there? There, the role of the internal symmetries come into the picture. So that's why at this point I am classifying the symmetry into 2 ways. Operator class, I would not say basis. I will come to when discuss the operators, then I'll talk about the basis. Okay. Well, yes, Lorentz scalar. Yes. So basically, you have these ingredients, okay, and you for every mass dimension, how many Lorentz scalar you can write down. Okay, it's not necessarily that all the operator classes are independent. So when you talk about these different kind of constants, that will be more clear actually. But at this point, we are not, worried about the redundancy in our structure. Okay, we'll talk about first our interest is basically to compute the whole invariant polynomial and then talk about the redundancy. Okay, yeah. Any other question? Okay. So now, based on this construction, we'll talk about the symmetry into two things. One is the space-time symmetry. Another one is internal symmetry. Now, among this internal symmetry, I'll classify into two. One is your gauge symmetry and the global symmetry. For example, sometimes your global symmetry can be accidental. For example, in the standard model, you have a global symmetry baryon number and lepton number. Okay, but they are basically accidental symmetries. You do not impose them. But why I'm talking about this global symmetry separately? That sometime while constructing the effective operators, we may be interested in some kind of rare processes, and those rare processes actually are there where I can violate a definite amount of global symmetry. So these constructions should be given in such a way that I should have a handle to pick out not only the invariant terms, okay, from the polynomial, but also I should be able to collect those operators which are possibly invariant under this gauge symmetry and the space-time symmetry, but violate the global symmetry by certain amount. Okay, so then if this method also provides you that picking out those operators, that will be a good add-on on this construction. Okay, so that's why I'm writing global symmetry differently, because this I am allowed to break and I can pick out those terms. Is that okay? Yeah.
It can be discrete or
no. Okay, it's a good point. So the construction is basically what I'm talking about, the continuous symmetries. Okay, because the discrete symmetries we will see it is more trivially done actually. Yeah. Any other question? Right. So now let's see with a small example how this symmetry can play a very crucial role. For example, let's say I have a real singlet scalar, okay, and then I am writing the Lagrangian in this particular form. Square, and I am writing up to dimension 4. Let's say okay, I'm truncating here. Okay, see if I have a real singlet scalar, I can write down all those terms. Now, as he has mentioned, discrete symmetry, let's impose a symmetry. The symmetry is basically I'm imposing phi going to minus phi. Okay. Now what do naively see that these terms actually are not invariant under this symmetry. So what is the role of symmetry then? The role of symmetry is basically you can have a multiple terms in the polynomial, and the symmetry when you impose, okay, through the transformation property of those fields, okay, they filter out some of the terms. So symmetry is basically putting some kind of constraints, okay, and that is how we have to use the notion of the symmetry in our construction. Okay. Fine. So let's start with one more example where I'm considering phi is a complex scalar, okay, where I'm saying phi is transforming as e to the power I theta phi, and theta is a global parameter, there is no space-time dependency, okay. So my conjugate of phi is transforming as this. Okay. So now if I consider that phi is not dynamical, okay, that phi doesn't have any kind of kinetic term, okay, so what kind of invariant term I can construct, which basically looks like phi star phi whole n, right? And this n is basically belongs to your n plus and 0. So I can have 1, which is field independent, but I can certainly add one thing, right? So now I can write down this polynomial which mimics certainly the invariant in the, under this transformation, and I can add all those terms and I can write it down as some infinity right. So this is like a collection of all the terms, and n goes from anything. Now you can see that if I assign this field some kind of mass dimension, okay, then what I can do some kind of power counting of these operators, right? So what is if the phi has a mass dimension 1, what is the phi star phi? Mass dimension 2, right? So then you can see that not all the Cn have the same mass dimension. Right? If I say this is part of my Lagrangian, which is a mass dimension 4, then you can see that Cn will need to be compensated by the suitable kind of mass dimension. Okay, and that's how you can do the power counting, and exactly similar power counting which we employ in the context of Smith. Okay, right. So now what is this Cn? This Cn not only gives you the proper power counting and this coefficient, but also it tells you that at given order n, okay, how many such composite structure you can form. For example, if I had 2 real singlet, for example, let's say, okay, so at the order n equal to 2, how many terms I could write? Phi 1 square, phi 2 square, and phi 1, phi 2, and if I assume that phi 1, phi 2 commutes, then let me omit this phi 2, phi 1. So you can see now at n equal to 2, I am writing 3 terms, right? Phi 1 square, phi 2 square, and phi 1, phi 2. So that means this C3 in this series gives you the multiplicity of the independent structures, okay, which having the same mass dimension. Like phi 1 square having mass dimension 2, phi 2 square 2, also phi 1, phi 2, 2. So now you can see, if I go back to what I was talking about operator class and the operators, I hope now it will get a better idea now. So for me, when I'm calling them, my operator class is phi square, right? My operator class is phi square, okay? But within the phi square class, there are 3 operators. So now you can see the first target is basically to understand what are the operator classes, and then what kind of symmetry I have, internal symmetry and other symmetries, that will decide that how many independent operators I can write down within that can be accommodated within that operator class. So C3, so this you can think of operator class, and the Cn is giving you the multiplicity of the number of operators within that operator class. Is that okay? Any question up to this part? Can you please repeat the question? Yes, so yeah, exactly. So this is the arbitrary way of writing the polynomial. Okay, so our target would be not only get these structures, but also we should have been able to extract the information what is the Cn. That means not only the operator classes, but within that operator classes, how many operators are there, independent operators, that is our target. Which one? C carries one more index means? Yeah. Yeah, okay, yeah. So on that is, so Cn is, you can think of a collection of those operators actually. Yes. Any other question? Fine. So now, that invariant that I have written here, okay, that can be written in terms of a series. And that series is basically well known to all of you. So you know what is this 1 minus x? We can add on as a 1 plus x square plus this way, right? So now let's mimic this x by phi star phi. Okay, so then I can write down this h phi star as a 1 minus phi star phi inverse, okay, and this can be written in a very interesting integral form, which is 1 by twice pi 0 to 2 pi d theta minus phi e to the power I theta 1 minus phi star minus I theta. Okay, so this series has an integral form in this particular. Now at this point, it is not very useful, right? I mean, okay, so I have a series, I am writing that in terms of, integral, but how does it matter? Okay, it will be more interesting when I'll consider z as unimodular complex variable, z equal to the power I theta, okay, and such that you can know 1. So this integral, automatically I can write it down as 1 by twice pi I integral mod z equal to 1 dz by z 1 minus phi z times 1 minus phi star z inverse. Okay. No, I am not talking about the convergence or anything.
So phi star phi should be less than 1.
I am not talking about the convergence of the series na, at this point. It will be eventually taken care of. Taylor expansion I can perform, but it need not to be convergent. But eventually when we talk about the effective field theory, that mass scale involved there, it will automatically take care of the convergence. Yeah, is another question? No. Okay, so now how do, and if you write down 1 minus phi z, 1 minus phi star z inverse, whole inverse if you write down, so what you can write down 1 plus phi star phi plus phi star phi whole square plus so on, okay, plus z times phi plus phi star phi plus so on plus z square plus phi square phi star phi plus so on plus 1 by z square phi star square phi star phi so on. Psi? Which one? Cn? Yeah. No, so okay, so for me, when I have a complex this thing, so all are basically C1, right? I have only this term. The multiplicity occurs only for the real singlet scalar. Which one? Yeah, I can always add a term which is take care of the scaling. So this is at this point, just forget about this to be kind of quantum field or something like that. This is just some complex variable. I can rescale my phi with some properly lambda, right? Yeah, then. So now let's look at this expansion. So you'll see there's a dz by z sitting here, right? And now from all this term, if you plug in back here, just from the residue theorem, you'll find out only this term is basically the non-zero contribution, right? So what you have learned that this expansion here, that using this, transforming this series into a complex integral, okay, so we can actually use this complex integral formula to pick out the invariant terms, okay, and that's the method we'll be using, okay. So in other way, if we have been able to write down or construct this quantity, okay, from a different mathematical technique. For example, here we have started with, we know this term is there, so we are writing this term in an integrand like this. But now, after doing this example, our statement is, if I have an independent mathematical technique or tool to write down this term, okay, and then if I perform this kind of complex integral, okay, and then this will offer me only to pick out those invariant terms. Okay, so let's see, apart from this expansion we have done to convince ourselves that this actually gives me this structure, these invariant structures. Okay, but this is like playing a side role here, just to convince ourselves explicitly that this integral really offers you those invariant operators, and which are not invariant, they are just dropped out because of the property of this complex integral. But one more lesson we can learn from here, what I was talking about this global symmetry. For example, if you assume that phi has some kind of global symmetry if we assign, then what are those terms? These terms certainly violate those global symmetry by some unit, right? And now what you can do, if you want to pick out the invariant terms, but there the global symmetry is violated by, let's say, by amount of q unit, okay, you can certainly scale this measure by that zq suitably, and then you will see the invariant term will not be this one but that one. So that's how this technique is powerful in that way. It's not giving you only the invariant term, but also you can tune your measure depending on what kind of global symmetry violating operators you want to pick. You scale your integral measure by the same amount of z, okay, and then eventually the simple pole will occur only for that q amount of violating the global symmetry terms. Okay, so that's how we can generalize this construction. But for the time being, we will focus on the invariant terms. Fine. Phi is a real scalar, that's a homework you can do, certainly. Yes. So we'll come up with a more generic structure. Okay, so now let's try to write down this 1 by 1 minus phi z times 1 minus phi star z inverse in a much more sensible way, which could be useful for us. 1 minus phi z times 1 minus phi star z inverse. This thing we can write down as a exponential minus log 1 minus phi z minus 1 minus phi star z inverse, and that I can write down as a exponential sum r equal to 1 to infinity phi z r by r plus phi star z inverse r by this thing. Okay, so this quantity I can write down in some exponential of some this kind of argument. Okay, so then how my h look like? It will be 1 by twice pi I mod z equal to 1 dz by z exponential r equal to 1 to infinity phi z r by r plus phi star z inverse r by r. This thing. Okay. So here let's identify that my integral measure is dz by z, okay, and this exponential what I am writing, this I define some special name which is called the statistics. Okay. So this is more like a generating functions. Okay. So I will come back to statistics later more for the time being, if you just have some name attached with that thing. Now, if we look at this quantity, that what we have learned from here, that okay, so there is a field phi which is transforming under, let's say this, where my q equal to 1, right? So this is, now let's have a rephrase of the whole game. I have a phi which is transforming under this e to the power I theta phi, okay, and I said that q equal to 1. You could set q equal to any quantity, okay, and then if it is so, then what I can do, I can construct a complex integral which gives me a series which looks like 1 by twice pi I is there, okay, it's a over modulus z equal to 1, say unit radius circle, and then dz by z is my integral measure, okay, and then there's an exponential, and in the exponential there is some kind of quantities are sitting. Let's have a detailed look into this structure. What is this? Phi z to the power r, okay. So this phi is basically, you can think of kind of a spurion. It's not like a quantum field or something like that. But as I told you that if you go back to this map where I talk about the Lagrangian, is nothing but for me to start with the symmetry invariant polynomial. Okay, so when I'm treating them as a mathematical object like polynomial, I don't consider them as a quantum field. I just think they're just like a variables. Okay, now how to translate those variables in terms of the quantum field, that is our last step. When we have these group invariant polynomials and we try to give them the structure of a covariant operators, that is our last step, and we'll learn about that thing. But our first target is basically to calculate the group invariant polynomials, and that's why this is just like a spurion variable. Okay, so there's a variable sitting there, and not only that, I can think of this z is nothing but z to the power 1. Okay, if I mimic in this way, that means the field which is transforming under some kind of a U1 symmetry, okay, and the U1 charge is q equal to 1, okay, and then I know it has some counter partner which is the complex conjugate field which is transforming as e to the minus q theta phi star. So I have now two variables, okay, phi and phi star, and for the phi is associated with some complex coordinates z, okay, and similarly the phi star, which is a conjugate, which is associated with the inverse of these coordinates, okay. And this, why the inverse? Because if you can think of the charge is q for phi, it is minus q for the phi star. So it seems like, you know, the phi z to the power q. This kind of combinations are there. Okay, so this is the intuitive way we can extract that information. So now, what is this? I mean, can we mimic some kind of mathematical properties with this kind of identification? Yes, we can do. This dz by z is basically, this integral measure has a special name. It's called the Haar measure, HAAR, okay, Haar measure, and this 1 by 2 pi I is like a normalization I'm using, so that if I take this d mu, that should be 1. This is the normalization I'm using. Okay, because dz by z will give you a 2 pi I, that 2 pi I both cancel from numerator denominator, I am getting 1. So this 2 pi I is basically for me the normalizations. Okay, and this z q is nothing but it's called the character of phi. So if there's a complex field phi which is having a E1 transformation with a charge q, I can define something called the character, okay, which is nothing but the z to the power q. That's all. Now you can ask me, okay, so why one variable, right? Why not z1, z2, z3, z4? So there I'll make a generic statement here that number of z will connect with something that you already know. Okay, so this number of z is basically your rank of this group that we are talking about. Okay, and this z is kind of a complex coordinate, right? And also you can think of as a E1 is basically like an abelian group. It's like a rotation, like e to the power I q theta, that is the rotation, right? Now what we'll try to generalize this thing, because we are not restricting ourselves to the only the abelian E1 symmetry, but for example, if I have to do for the standard model, what are the other symmetries we have? SU2, SU3 and so on, right? And SU2 and SU3, they are certainly have some kind of non-abelian nature. Okay, so then we have to learn that how we can generalize these two quantities, hard measure and the character, corresponding to different kind of representations of those different groups. Okay, so what will be our primary focus? So primary focus will be on the connected compact group. So the construction that we'll be talking about will be for the connected compact groups. And now it may automatically create some kind of curiosity in you that if you come back to this point, symmetry. Symmetry, when I'm talking about the internal symmetry, generally in the context of SMAP, we are dealing with the gauge symmetry, the global symmetry. They are compact groups you are talking about. But what about the space-time symmetry in the 3+1 dimension? Is it compact? No. Right? So then the method that first we'll discuss will not be readily applicable to deal with space-time symmetry. But can we ignore space-time symmetry? No, because at the end of the day, the Lagrangian that I'll be writing, right, that has to be also invariant under the Lorentz symmetry. And also we have to deal with the quantities, forget about this one, but I have a fermion, I have a d mu, I have a f mu, which transform non-trivially under the space-time symmetry. Okay, so to take care about their transformation and making them invariant term, so I need to learn how I should be able to write down the characters for this kind of thing, okay, with a modification of the method that I am going to introduce. Okay, yeah, any question up to this part? Yeah, yes. So yeah, but exactly, you are absolutely correct. We do that thing that way, but we'll try to do something. What I'm going to in the while thing actually, we'll construct in that while notation SU2L cross SU2R, and because that group will also be important when I talk about the redundancy, equation motion, all those things. So within Lorentz group will not be sufficient for us. We have to extend that group. Yeah. But yeah. Any other doubt or any question up to this part? Is it clear? Okay. So now, before going into this, these generalizations to, non-abelian groups, specifically our primary interest will be on SUN, because that's what our primary target, as I told you, to SMEPT. But again, this method will be equally applicable for this kind of group. Okay, but this will not be of our current interest. We have to revisit this one when I talk about what he has pointed out, that when we talk about the Lorentz symmetry, how to calculate the characters for that thing. Okay. So now, the question is really, why certainly? Because when you talk about the standard model Lagrangian, so then we didn't need to talk about these characters or Hermezar or group space integral and all those things, right? What we used to do, we know what is the symmetry, I know what is the representations, okay, and we try to do something called the Young tableau, the tensor products kind of thing, to check whether the operators are group invariant or not. For example, if I have to check for SU2, now the SU2 2 cross 2 gives me 3 plus 1, right? For 3 cross 3 is 5 plus 3 plus 1. So we'll always look for those representations and try to take a tensor product of them such that at the end of the day I can create a singlet, which is this one or not. So for SU2 it is pretty simple, because you can mimic that thing with in your background, that addition of angular momentum. But also this Young diagram technique also equally applicable for your SU3, right? So for so this is for SU2 we used to do. Now for SU3 we have this 3 cross 3 is 6 plus 3 bar, 3 bar cross 3 is 8 plus 1, and so on. So we have those informations and we check individual term picking out by the representation they are singlet or not. But when we want to calculate those effective operators, they are higher dimensional operators first of all, okay. That means the number of fields appearing in those individual operators are more. For example, it's like a tedious task to check explicitly whether they are forming a singlet or not. One thing. Second point, because the number is growing exponentially large when you go beyond dimension 4, okay, then you may miss out some of the operators, okay. Or also you can overestimate. I mean, you can write down 2 different operators without knowing they are same or not, okay. So this kind of manual prescription we want to avoid, where we have to deal with and construct the huge number of operators. And that is why the reason that our known method, okay, will not adapt. We'll try to adapt a more simpler, in a sense, it's a new language, but once we adapt that thing, that gives us better handle for that thing. Okay? So that's why what we'll try to do, we try to first learn how to calculate the characters of SUN representations. Okay. So now, without going into very mathematical details and argument and all those things, how we do that, I'll just make a map of these SUN groups with its maximal torus. Okay. And what is this maximal torus? Naively, what you can think, if SUN is the group you are interested in, what is the rank? n-1, right? So it is basically the maximal torus is basically Tn-1. What you can write down, n-1 copies of E1, product of that. Okay. So SUN you can think of as a maximal torus Tn minus 1. This is how we'll write down, and this is actually E1 times E1 times E1 in minus 1 copies. Okay, and if you are interested in UN, okay, you have its rank is n, so it's like a n copies of U1. That's all. Okay, so now once we do that, what we can do, we can calculate the character of these representations, okay, in terms of this torus coordinates. Now you can see this E1, so there's only one E1, so I have only one Z, right? So now for SUN, I have how many E1s are there? N minus 1 number of E1s are there. So for each E1, you will introduce a one unimodular complex number. So effectively you have a n minus 1 number of complex variables, independent complex variables, right? So we will write down these characters, okay, in terms of those complex coordinates. Okay. So now character of what? That is the question you may ask, because E1, in case of E1, it was not there. Because why? Because E1 doesn't have any representations. It has only charges. But now starting from SU2, SU3 and so on, they have different kind of representations, right? For example, SU2, I can have a 2-dimensional representation. I can have a 3-dimensional representation. For SU3, I can have different kind of irreducible representations, right? So there will be one-to-one mapping we'll try to set up, that for each representations, I will try to write down the character functions. Okay. So the target would be to set up the relation between the representations and the character function. Because we have seen that we used to deal with the representations when we have a better handle over the young tableau, right? But we cannot certainly do this thing here because it's very tedious and almost erroneous, I would say sometimes. So to adapt this kind of or create this kind of environment for a general group, compare group, we'll try to realize those representations in terms of their character functions. Okay, so that's why we have to learn how to calculate the character function for any given representations. Okay, yeah, up to this part, any question? Okay, okay. So now, what we'll use, what while has provided us, the while character formula. So you must be noted somewhere, okay, so character is given as a trace of some irreducible representations and so on, but I am not going to use those definitions, but rather I am going to give you a very simple matrix way to calculate the character, because we cannot just use the definition for our purpose. We need to really calculate those character functions explicitly. That's why we'll calculate the character. So let's say any irreducible representations I'm considering M, okay, and the character is given as, let me write down and then I'll explain. One, okay. So this is a ratio of these two determinants. Okay. Now, how do you write down this thing? This first numerator, which I'm calling as a n tilde, is written as epsilon 1 r1, epsilon 1 r2, up to epsilon 1 rn minus 1, 1, then epsilon 2 r1, epsilon 2 r2, epsilon 2 rn minus 1, 1, and then so on. And this is epsilon n R1, epsilon n R2, epsilon n Rn minus 1, and then 1, right? So this is the numerator. So this is the, if you calculate the determinant, we can compute. And what is this epsilon? The epsilon are basically these maximal torus coordinates here, and the property is basically A equal to 1 to n epsilon A equal to 1. So this is the condition on these epsilons. Okay. And then we have to calculate the denominator also, which I am calling as d tilde, which is written as epsilon 1 n minus 1, epsilon 1 n minus 2, epsilon 1 1, and then epsilon n n minus 1, epsilon n n minus 2, epsilon n. Okay. So now let's try to understand what is the difference between this numerator and the denominator. Okay. So this, I am writing this character for a given irreducible representations. Okay. So then look at the denominator. So these epsilons, once I know what is my group and I know what is this maximal torus, so I know these torus coordinates are there and epsilons are constant like this. So now I can write down the denominator like this, right? Now for SUN, this n is fixed. For example, for SU2, this n is 2. For SU3, n is 3. So then, in this context, there is no information where the representation dependency will be reflected. Because if you think about, here the epsilons are same for, if I consider SU2 or SU3, these epsilons are same irrespective of the representations. This n is fixed irrespective of the representations. So there is no representation dependency in the denominator. Okay, and this is called the Van der Monde determinant. This denominator, which is the important statement, is independent of the representation, and this, when I talk about the construction of the Haar measure, again we'll use this quantity, and that is quite obvious because Haar measure is a, so let's make it very clear. Haar measure that I am defining here, which is the integral measure in the group space, is basically nothing to do with your representations. Once I fix the group, the Haar measure for this group is unique. So that can be written in terms of some quantity which does not have any representation dependence. And this quantity is not representation dependence. So the Haar measure, when I'll compute, I'll show you that this d tilde will appear in the construction of the Haar measure. But now you must be wondering that when you talk about the representations, Rick, how much time I have? 10 minutes. Okay, thank you. So now, so when I talk about the representations, you may ask me, okay, so you talk about the representations which are independent, right? SU2, 2, 3, 4, for SU3, there's a 3, 3 bar 8, they are independent. So then, if I calculate the character and you are saying that, okay, so characters for the given representation, there's a 1-to-1 correspondence as of now, right? That means they are in this quantity, there will be somewhere the representations dependency is hidden, right? Where is that? That is these quantities, Ri. So this Ri is the variable where the representation dependency occur. So that means all these character functions for a given representations I can compute if and only if I know how to calculate this R. Right? So I'm giving you representations, okay, and if I ask you to calculate the characters, this quantity you know, which is independent on the representations, epsilons you know, okay. What is different for different representations is this Ri's. That means these Ri's I should be able to write down in terms of some variable where the representation dependency should be reflected. Okay. Yeah, any question up to this part? Yes. Yes, yes. That means basically all the epsilons may not be independent, right? Yeah. So I have a n number of epsilon, you are correct. But I am not demanding all the epsilon, so that's a constant, right? That constant remove, there's one constant, so remove is basically n minus 1, right? Good. Any further question? Yes. Yes. So that means basically if our statement is correct that the representations and the character function that one-to-one correspondence, that 3 and 3 bar are conjugate with each other, that should be reflected when you calculate the characters for them as well. Right? So that we'll explicitly check. Okay. Any further question? Good. So now at this point we'll take a pause and then we, as he has pointed out correctly, that I am supposed to work in a basis where my torus coordinates are n minus 1, but I am working n. That means I need to go to that basis, right? And what is that my basis? Basis is basically this unimodular this thing z. So I should have a z1 to zn minus 1 variable which are nothing. So my zi's are nothing by e to the power I theta I, right? Where I equal to for SUN runs from 1 to n minus 1. So then I should have give you the prescription how these zi's and these epsilon i's are related to each other. That means I have to perform a change of basis, right? So how do you do that thing? To do that, what we have to take the help of something called the Cartan matrix and Dynkin diagram. So if you know the Cartan matrix, you can draw the Dynkin diagram, or if you know the Dynkin diagram, from there you can write down the Cartan matrix. Okay. So now, what is the Dynkin diagram for SUN? It's basically very simple. You just have a n minus 1 number of nodes. So this number of nodes are basically n minus 1. Okay, and then you can immediately write down the Cartan matrix for this SUN, which I'm denoting as A, which is basically 2 minus 1 minus 1 2 0 0 minus 1 minus 1 2 minus 1 minus 1 2 and so on, 2 minus 1 minus 1 2 0 0. And how to map this thing? That basically you can see that only consecutive nodes are connected with each other. Okay, and there's a 1 represent the one handle is there and 2 represent one blob. That is the pictorial way you can do this thing. But of course there is a mathematical way of constructing this thing, so let's not go there. So there I have written down the Cartan matrix for this thing. Okay, so then what we will try to find out something called the fundamental representations of SUN. So for SUN or any this given group, how many fundamental representations are there? Rank n minus 1. So you for SUN you have n minus 1 fundamental representations. But so how do you write down the Dynkin level for the fundamental representations? So Dynkin level for the fundamental representation write down as a 0p 1 and then 0 a3, sorry, q, something like that. Yeah. Okay. So then instead of all this n minus 1 fundamental representation, the one which is of our interest is the lowest dimensional fundamental representation. Okay, or in we call this LDF. Okay, so among this fundamental representation, we look for the which one has the lowest dimensional fund. For SU3 it's a 3, okay. For SU2 it's a 2, for SU4 it's a 4, and so on. Okay. So now the lowest dimensional fundamental representation, the Dinkin level, is given as 1, 0, 0. Okay. This is how much? N minus 1. So n minus 1 number of entries are there. Okay. Can I take 5 minutes? Huh? Okay. Because I just want to finish one step. Yeah. Okay. So once you have this this quantity, so this I define as my L1. Okay. And then what I'll do, I'll calculate something called the L2, which is L1 minus alpha 1. And what is my alpha 1? Alpha 1 is nothing but my this row. So I have alpha 1, alpha 2, alpha 3, alpha 4, and so on. Okay. So now you can see I can calculate this continuously until I reach this quantity. Okay. So then once we compute this part, I can use. Yeah, once I compute this part, then any Li, I should be write down to as Li1, Li2, Li3, so on up to Li n minus 1. It's like a n minus 1 tuple vector I can write down. So you just pick any L1, so I will be 1, and then so you just subtract them and you find out what is your L1, L2, L3, just construct. Okay. And then this relation will give you the relation among the epsilon and z. 2 times Zn minus 1 Li n minus 1. So now, once we have these L's, so using this relation, I can go to construct a relation between the epsilons and the z. And if you do it carefully, what you should be able to find out that epsilon 1 equal to z1, epsilon 2 equal to z1 inverse z2, and then so on, and epsilon n equal to zn minus 1 inverse. Okay. So now you see, I had n epsilons which are not independent, but all these n epsilons I am writing now in terms of n minus 1 number of z. So now I am going to a basis where all the z's are independent. So I have removed that redundancy term. Right? So now I should be able to compute this n tilde and d tilde in terms of epsilon first, and then using this relation I can rewrite that whole polynomial in epsilon in terms of z. Okay, so this is how you write down the characters in terms of a torus coordinates, which are basically independent coordinates now. But still one thing is left, that is how to calculate the Ri's. And once we do that, then only we will be in the position to compute the character for any SUN representations. So I think it's a time to stop. And please check this relation, because this is the kind of a homework you can do actually. Set up the relations. It's just the fill in the blanks kind of thing. Nothing more than this. It's just high school level algebra. Okay, yeah. Or if they can have some quick question.
Yeah, if you have any question.
Yeah, yeah. Mm-hmm. Yes.
But that was possible only because you had mod z as 1. If suppose if I have scaling and phi goes to a phi,
Okay, so for example, what the symmetry I'm talking about, just let's stick to that, because I don't want kind of unnecessary discussion which is not relevant for me. Okay, yeah. Any other relevant question? The scaling symmetry, I talk about for the non-compact group connected one. I'm talking about. Yeah, so that is not part of that thing, right? Yeah. Highest weight state, yeah. Subtracting the row of the Cartan matrix, and this is the, okay, so as you have pointed out, so this is the whole thing called the weight tree. We are creating the tree starting from the highest weight by subtracting the row of the Cartan matrix. So for any representation, you construct the highest weight and you subtract this thing and you construct the weight tree for that. Yes. But in this case, this gives me a better handle to go from epsilon to z basis. Yeah, I can understand it's a new language probably for them, so take time to digest. Yeah, but feel free to catch me any point of time.